Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at a problem from homework 5a, which covers over the concepts involving uniform circular motion. Specifically, we'll be looking at an analysis of an object moving in a circle and doing some work with the equations that we've been learning here in this unit. This problem is not going to have the same values that you see on your assignment, but the concepts will be the same, so make sure that we pay attention that the numbers I use are not going to be the numbers that you will be using. Our problem says this: an airplane flying in a horizontal circle is flying in a horizontal circle at a speed of 50 meters per second. The 79.8 kilogram pilot does not want his radial or centripetal acceleration to exceed 5.51 Gs. The acceleration of gravity is 9.8 meters per second squared. What is the minimum radius of the circular path? Now, if we're looking for a radius, we need to maybe begin by asking, what equations do we have where the radius term shows up? So we have an equation for the velocity of an object moving in a circle. Its circumference over the period, our radius term is here. Centripetal force, a force directed inward into a circle, is equal to mass times velocity of the object squared divided by its radius. And then lastly, centripetal acceleration is velocity squared over the radius. Now, looking at the problem statement, I don't actually know anything about times. I'm not given those, so I'm probably not going to use this first equation. But the second two are a bit of a mystery, right? We know the mass, we know the velocity, but we still have two things missing in this equation for centripetal force. And here, all we know is the velocity. So again, still two things missing. So just by looking at what the problem statement gives us, we know the velocity to be 50 meters per second, and we know the mass of the pilot to be 79.8 kilograms. But we're told this other piece of information, that the pilot does not want his radial or centripetal acceleration to exceed 5.51 Gs. So what that means is that the G-force limitation on the pilot, A, is 5.51. Now, that G-force actually has a relationship to centripetal acceleration. Remember, a G-force is not a force in the regular way we think about forces. It's really a ratio of accelerations. And oftentimes, that idea of G-force can help us understand if conditions are safe for human beings, right? Because if the G-force on something like a human body gets too high, then that can lead to some very bad physical effects. Usually it starts with something small like dizziness or maybe a little bit of nausea, but then that can escalate to unconsciousness, even possible brain damage or heart damage, depending on your body, your age, and how long you're subjected to that amount of G-force. So here we know that the G-force cannot exceed 5.51 Gs. And so with our equation, as well as with local acceleration due to gravity on the Earth, then we can actually find what our centripetal acceleration would need to be. So here we go. Our G-force, actually I'm going to do this in a slightly different color. In fact, I'm actually going to come down and give myself a little more space so we're not too cramped. G-force is the centripetal acceleration over our local acceleration due to gravity. So we're told the maximum G-force is 5.51 Gs. That's equal to our centripetal acceleration divided by 9.81 meters per second squared. Now that I'm here, I can actually pretty easily rearrange to get my centripetal acceleration. Just multiply by 9.81 onto both sides of my equation here. So these values will cancel out, and I'll be left with an expression just for our centripetal acceleration. 9.81 meters per second squared multiplied by 5.51 Gs. That's going to give me about 54.05 meters per second squared. So now I have my centripetal acceleration, and I can use this along with my velocity to find the radius that we're looking for. So here, now, my centripetal acceleration is v squared over the radius. So I want to get my radius term by itself, but it's in the denominator, which means I've got to multiply it to get it up to the numerator. But whatever I do on one side, I have to mirror on the other to keep the balance in my equation. So r divided by r, those terms will cancel out. And now I can divide by my term for centripetal acceleration, a sub c. Again, we're trying to get r by itself here. So now we've got an expression just for r. Our radius is equal to our velocity squared divided by the centripetal acceleration. So now we can plug in what we know. We were given at the beginning of the problem the velocity of our object, 50.7 meters per second. We'll square that value, divided by our centripetal acceleration, which we just found, 54.05 meters per second squared. So now I will plug these values into our expression, and I'll get a value for the radius of 47.6. That will be meters. Now, the problem says, what is the minimum radius? How do we know this is the minimum? Well, the problem tells us that the maximum g-force is 5.51 g's. So imagine if we were to all of a sudden make our radius, let's say, bigger than this value, larger than 47.6, well, look at our equations, right? If we make our, come back up here, well, actually, we'll use it down here. If we make our radius, think about the centripetal acceleration, we square it over r. If I make my radius bigger, my denominator goes up, that's going to mean this number goes up. If my velocity stays the same, my centripetal acceleration will go down, which means I'll have less g-force on the pilot, which would be fine. So it doesn't really matter if we increase our radius here, because that's going to decrease our g-force. The problem is if we decrease the radius. Because if we decrease the radius at the same velocity, that's going to increase our centripetal acceleration. Those values are inversely related. Okay? Less radius at the same velocity, greater centripetal acceleration, so we'll have greater g-force on the pilot. So this value here, because we use the maximum g-force, it's going to be the minimum radius we can have. Otherwise, if it gets smaller, it's going to exceed that threshold for g-force. So hopefully this gets us moving in the right direction for this problem on your homework. Remember, as we're working through these problems, ask yourself, what am I looking for? What does the problem want from me? What am I given? Right? What numbers does the problem provide me with? And then what equations do I have that can help me get from what I'm given to what I'm looking for? Right? Hey, using that idea is going to be really helpful in narrowing our focus, to figure out what exactly we're going to do. So there is the second part of this problem that reads as this. At this radius, so this value, what is the net or overall centripetal force exerted on the pilot by the seat belts, the friction between him and the seat, and so forth? So really it's asking us, what is the centripetal force on the pilot? Now the reason it says net or overall force, and the reason it mentions the seat belt and the friction between the pilot and the seat is this. There might be several things that are actually pushing on the pilot, helping the pilot move in a circle. And when it says net force, it means taking all of those forces into account, what is the overall centripetal force based on the numbers that we know. So, we're going to use the numbers that we were provided with as well as what we found. The mass of the pilot, 79.8 kilograms. The velocity of the pilot, which is the same as the velocity of the plane, 50.7 meters per second, quantity squared. And now the radius that we just found, 47.6 or 46.7? 47.6. Good, just to double check. Meters. So now we can plug in our values to our equation for centripetal force. 79.8 multiplied by 50.7 squared divided by 47.6, and we end up getting a value, F sub C. Actually, hold on. Is it 78.9 or 79.8? 79.8. There we go. And just to double check, we get about 4309. And that would be newtons. Here we go. So really the last part of our problem is just a one-step extension of what we've already found. Once we have the radius, we have all the pieces we know to find our centripetal force. So hopefully this gets you moving in the right direction on this problem. Make sure we're in the habit of reading our questions carefully and analyzing what the problem gives us to help us solve for what we're looking for. As always, if you have questions, make sure to come and ask them. I'm happy to work with you if you need help. Good luck.